Okay, so you should see a screen that says 1905 Einstein's Annus Mirabilis. Um, so this presentation I've actually given it at a number of RGs, and I was going to give it at the AG this year, but as obviously I won't be doing that. It's a 90-minute presentation. The first half of it, which we are not going to do today, is related to radiation. What is radiation? How does it come about? That sort of thing. And then from there, we get to black body radiation, which then leads into Einstein's miracle year of 1905 and some of the technical papers that he published then. And then we take a deeper look at a few of those papers and some of the strange things that you find in the paper. So that's what we're doing. We are beginning in medias res of this presentation. We're going to begin with discussion of Einstein's 4 technical papers in 1905. But before we do that, I'm going to take one small step backwards to the slide. Let me see, why is that not? There we go. The slide that talks about black body radiation. There's one point that I need to make from this slide, and that is that all baryonic matter gives off energy. Baryonic matter is you, it's me, it's the floor, it's the roof, it's the sun, it's the planets, it's everything that you can see. Everything that you know of, all matter, gives off electromagnetic radiation. And that electromagnetic radiation that it gives off is based upon the temperature of the object. You and I are about 300 degrees Kelvin. So we give off electromagnetic radiation in the infrared scale. That's why they have those heat sensing cameras that can detect you at night, because you're giving off electromagnetic radiation in the infrared scale, and the cameras can see infrared radiation. Something like the sun, which is 3,000 degrees Kelvin, gives off electromagnetic radiation in the yellowish, plus a bunch of other colors, which tends to make it white. It's a very broad spectrum from the sun. So as you know, like I said, all matter in the universe gives off radiation. The frequency or the wavelength of that radiation is just based upon the temperature of the object. So with that in mind, let's jump ahead to the first of the 4 papers we're going to discuss. And this one we're going to spend very little time on. Einstein wrote one of the first papers in 1905, had to do with the Brownian motion in liquid. What he basically did is he took the kinetic theory of gases and he applied them to liquids. The reason that was so strange is because the atom had not yet been invented at the time. It hadn't been discovered. People were suspicious that there was something called an atom, but they weren't certain of it. And what Einstein was able to explain was that the rules that apply to gas are the same rules that apply to liquids, because they are made of the same things, which are called atoms. So that in itself probably could have gotten Einstein a Nobel Prize, but it didn't. The second paper I want to talk about is the photoelectric effect. It was well understood in 1905 that if you had a piece of metal and you shined a light on that piece of metal, that the metal would sometimes absorb the energy from the light and it would shoot an electron off. It would actually generate electricity. So you point light at metal and all of a sudden electricity happens. These electrons shoot off. But sometimes it wouldn't happen. And there was really no explanation at that time for why some light would do it and other light wouldn't. So what Einstein did in his paper on the photoelectric effect was he took this sheet of potassium and he shined a red light on it. Red is an electromagnetic radiation in the 700 nanometer range. And what happened is, for the potassium, that red light would just bounce right off. It didn't matter whether it was a very dim light or a very bright light. The light would just bounce right off of potassium. When he shined a green light on it, which is in the 550 nanometer wavelength range, the potassium would actually absorb some of that light and it would shoot off some electrons, but not a lot. And when he shined a blue light on the same potassium, it would absorb almost all of the energy and it would shoot off electrons at a very high energy level, even if the blue light was very dim. And from that, Einstein was able to explain that the light is actually packets of energy. Um, it is electromagnetic wavelengths, and it has no matter to it whatsoever, but it is basically pure energy moving at the speed of light. And so there was a great debate in the scientific community whether light was a wave or it was a particle. And what Einstein was able to prove was that the light was simply a packet of energy. It had no mass. It was not a piece of matter. An interesting side note is there was a physicist who was a peer of his at the time named Robert Millikan, who was convinced that Einstein was wrong, that his paper was completely and totally off. He was convinced that light was actually matter. And so he set about his goal to prove Einstein's photoelectric effect paper was incorrect. What he ended up doing 15 years later was he ended up proving that Einstein was in fact correct, that everything in the paper was right. And together, Einstein and Millikan won the 1921 Nobel Prize for Physics. It was the only Nobel Prize that Einstein ever won, and it was given to him for his paper on the photoelectric effect and other advances in science. Einstein was not a very popular person, and the Nobel Committee wasn't really inclined to give him any Nobel Prizes. So they did end up giving him one, and they kind of took all of his life work and just put it together. They could have easily given him 4 or 5 Nobel Prizes based upon the other people who had gotten Nobel Prizes and the things they got them for. And so that was his second paper in 1905. The third paper had to do with mass energy equivalence. Do you remember when I first started talking about the black body radiation, I said all baryonic matter gives off energy. Well, this kind of bothered Einstein because if something is giving off energy constantly, it has to be losing something. Now, the easiest thing is to say, well, I'm absorbing energy and then I'm going to give off energy. But it was true that if there was something that was not absorbing energy, if you had a piece of matter that was out in the middle of nowhere in a perfect vacuum and there was no energy for it to absorb, it would still be giving off energy. And so Einstein thought that he could calculate what was going on. How are you losing energy? If you give off energy in the form of radioactive, of electromagnetic radiation, are you losing some other kind of energy? Are you losing some inertial energy, or are you losing momentum? What? And as it turned out, he figured out you're losing mass. The more energy that you give off, the less mass that you have. And so the name of the paper was, Does the Inertia of a Body Depend Upon Its Energy Content? And in the paper, what he theorized, or actually what he proved, was that if a body gives off energy in the form of radiation, its mass diminishes by the energy, which is L, divided by the speed of light squared. Of course, he wrote it in German because it was a German paper, but nonetheless, that was the sentence that was kind of the summary of his paper. And if you take that sentence that he wrote in German and you convert it to a mathematical formula, you get the mass is equal to the energy divided by the speed of light squared, or in our common English phrase, E equals mc squared. Energy is equal to mass times the speed of light squared. So what he was basically saying is that as matter gives off radioactive energy, if it's not absorbing any, then it must be losing mass. And in just a few minutes, we're going to talk about some of the strange effects that actually causes and why that's a very weird thing to say. And before we get into the fourth of Einstein's paper, there are 2 scientific terms I just need to describe rather quickly. The first has to do with something called an inertial frame of reference. Very important because we're going to talk about Einstein's theory of special relativity soon, and this is the frame of reference is critical. So if I were to ask you if your floor is moving right now, I think most of you would say no, the floor is not moving, nor are the walls or the ceiling or anything like that. They are all fixed and stable. Now, obviously, this is Mensa, so probably one of you is going to say it's moving just because it's Mensa. But nonetheless, that is an absolute correct statement to say. If you tell me that your floor is not moving right now, you would be 100% correct, because within your frame of reference, it is not moving. Now imagine for a second that there was an astronaut that was at a fixed point in outer space, fixed in reference to the Earth outside of our atmosphere. So that astronaut is looking down at the Earth spinning. If I ask that astronaut the same question, is the floor moving? The astronaut would say, well, the Earth is rotating at 1,000 miles an hour, and the floor is attached to the Earth. So therefore, the floor is in fact moving at 1,000 miles per hour. It's on the Earth is spinning. I can see it. Boom. So that astronaut would be absolutely correct. The astronaut would say the floor is moving at 1,000 miles per hour. Now, if there was a second astronaut, and the second astronaut was at a fixed location outside of our solar system, looking down at us, they would see the Earth orbiting around the sun, and they would see that the Earth is moving at about 66,627 miles per hour as it goes around the sun. So that astronaut would say that the floor is in fact moving at 66,627 miles per hour, and at the same time it's spinning at 1,000 miles an hour. And then if there was a third astronaut, and he was outside of our solar system, he would see outside of our galaxy, the Milky Way galaxy, he would see that our solar system is in a spiral arm of the galaxy, and that in that spiral arm is rotating around the center of the galaxy, the big black hole at the center of the Milky Way, and it is moving at approximately 448,000 miles per hour. So that astronaut would say that the floor is moving at almost 500,000 miles an hour, and that astronaut would be correct. So all four of those individuals would be correct because they're answering the question from their frame of reference. There is no center to the universe. There is no fixed point in the universe. There's no place you can go to say, this is sitting still and everything else is moving. The entire universe is constantly moving. Everything is moving in relation to itself. And in fact, the universe itself is expanding at faster than the speed of light. And so there is no way that you can say this point is fixed and that one is moving. The only thing you can say is, I'm going to choose this point and I'm going to call this point the fixed point. And then all of my experiments are going to be assuming that this is the fixed point, and everything that isn't fixed with it must be moving. It sounds kind of weird because you could say, if I had an apple in my hand and I let the apple go, it would be perfectly valid to say that the apple fell down to the earth, and it would be equally valid to say that the earth fell up to the apple, that the apple did not move at all. That is because when you're doing any physics experiment, you establish a frame of reference, and then all of the calculations are based upon that frame of reference. And there is no preferential frame of reference anywhere in the universe. The second science term we need to talk about is the speed of light in a vacuum. Technically it's 200, the most accurate calculation so far is 299,792,458 meters per second. So I will always use the calculation, the approximation of 300,000 kilometers per second. Kind of an interesting backstory. The first estimate of the speed of light was actually done by a Danish astronomer named Ole Rømer back in 1676. He was studying the moon Io as it goes around Jupiter, and he was noticing that when it was behind Jupiter, he couldn't see it. It was black. When it was in front of Jupiter, it was white. He could see it. So it would kind of be like blinking on and off. You'd see it, not see it, see it, not see it. Not only that, but he noticed that the timing of seeing it, not seeing it would change. Sometimes of the year it would be going very fast. Other times of the year it would be going slow. And so he theorized that the reason for that is because sometimes the Earth was moving toward Jupiter. And so he would see the light quicker because it would be reaching him faster. If you're familiar with the Doppler effect, you'd be getting to the light quicker. And sometimes the Earth would be moving away from Jupiter, so it would take the light a longer time to actually reach Earth. And so he basically, in 1676, using only this telescope and writing down the times that he was able to see the moon Io, he estimated the speed of light to be 220,000 kilometers per second. So he's basically off by about 26%. But again, this is 1676 when he's just doing things basically with hand calculations. The one thing I want to note is we talk about the speed of light in a vacuum. There is no place in the universe that is a perfect vacuum. Even if you go to the depths of outer space where there's the absolute nothingness, you still have all of this background, the background radiation from the Big Bang, and you have cosmic rays that are shooting through. So nothing ever actually goes exactly the speed of light. It always goes a little bit slower because there are always things to interfere with it. But for the purposes of our talk today, we're just going to say that all light travels at the speed of light in a vacuum, which is roughly 300,000 kilometers per second. So now let's get into special relativity. So Einstein, when he was looking at the movement of this electromagnetic radiation, he was wondering the impact that it had on matter and how matter moved through space. He was studying the works of Isaac Newton, and Isaac Newton, when he did his studies, he had a very difficult problem because he was studying space and how things move through space, but he didn't tie together the concept of time, and he knew that he had a problem. So Isaac Newton solved the problem by saying that space is one thing and time is something else. They are two completely different things. And so he created all of his calculations on space and saying that no matter what you're doing with time, it does not affect that. Einstein didn't like that. Einstein knew that there was something wrong with that, that the relativity that Isaac Newton was using incorrectly ignored time. And so he said you need to somehow figure out the elements of time, especially when you're calculating the speed of light, because light moves at the fastest speed of anything through the universe. And so on his paper on special relativity, he started with two very simple statements. His first was, the laws of physics are invariant in all inertial frames of reference. This was actually proved by Galileo Galilei in the 1600s. Galilei was the first one to actually invent the concept of relativity and to document it and to write a book about it. But again, Galilean relativity was for space and not for time. What Einstein did was he added a second level of complexity. What he said was that the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. Now, on the surface, that sounds like a very simple thing to say. Light always moves at the same speed. Sure, it makes sense. Absolutely. But what we're going to do now is we're going to look at some strange cases where when we understand what that means, it gets really weird. So with that, let's start with E equals mc squared. One of the things that you probably already guessed about the outcomes of E equals mc squared is an atomic bomb. That you can take 11 pounds of plutonium, which basically is enough to like fit in your hand, and you can destroy an entire city. Because with those 11 pounds of plutonium, you take the mass of that and you convert it into energy, and you can actually, like I said, you've got an atomic bomb and you're destroying a city. An interesting fact about Einstein is he was a pacifist. He hated war. He hated anything having to do with war. He hated weapons. He was actually rather simplistic. Sometimes he was communist, sometimes he was socialist. He was just always he was always in favor of being good to people and being helpful. But he actually wrote a letter to President Roosevelt in 1939 and had it delivered through a secret back door. The ambassador to Belgium had to get it to him. And he basically begged President Roosevelt to make the atomic bomb, which was very much unlike him. But the reason he did it is because he knew that if the Americans didn't get develop the atomic bombs, that the Germans would have, and that the consequences would have been far worse. So luckily, Roosevelt got the letter, he developed the bomb, and we know what happened, except all the bad parts of that. But let's look at another effect of E equals mc squared. If you take two pocket watches, like the ones pictured on my screen, and they are identical and neither one is wound. And when I say they're identical down to the atomic level, like completely and totally identical. If you weigh those two watches, they will weigh the exact same amount. They will show the same thing on the scale. If you take one of the watches then and you wind it and you weigh it again, the watch that is wound will weigh more than the watch that has not been wound, because you've been adding energy. You've added potential energy in the springs when you wound it. You've added kinetic energy of the dials as they move. You've added heat energy from the friction of the different gears as they go. And all of these energies directly affect the mass of the object. And so what that's basically saying is the more energy that you add to an object, the more mass that object has. Now, if you want to get really weird in science fiction-y, you might say, well, theoretically, what if there is no such thing as mass? What if all of the mass is really just energy that is floating around and is, you're adding this energy and you're congregating it into a location. And so that is what basically mass is just energy that's congregated into a location in space. And then, of course, that again leads to the holographic principle that says, well, if that's true, if we're nothing but energy, maybe we're just a bunch of numbers in a computer that says where the energy is, and we're just, it's everything else is just in our head. But unfortunately, we don't have time today for the holographic principle. Perhaps we'll get to that in another talk. Let's keep going now, back with Einstein's theory of special relativity. The basic statement, the speed of light in a vacuum is the same for all observers. Okay? I want to give you two examples so you can understand the difference between Galilean relativity and Einstein's special relativity. We're going to start with Galilean special relativity. Imagine that there is a train going on a track at 100 miles an hour, and it is perfectly smooth, no bumps, no changes in speed, 100 miles an hour. Bob is inside the train, but he can't see outside the train. The walls are opaque. He cannot see through them. So he really has no idea how fast the train is going. As far as he's concerned, he's not moving at all because he can't sense any changes in his motion. And he has a flashlight in his hand, but the flashlight doesn't work. And so he's angry and he throws the flashlight in the direction that the train is traveling. Okay? Now, at the same time, while Bob is doing this, Bob is inside the train, Karen is outside the train sitting at the train station. And Karen is watching the train goes by, and somehow magically she can see through the walls of the train. So she can see that Bob is inside the train, and that she can see Bob throwing the flashlight in the direction of the train, and the flashlight is moving at 25 miles an hour away from Bob. So if I ask Bob how fast he is going, his answer would be 0. I am not moving, because he cannot sense any motion whatsoever. He's going at 100 miles an hour, perfect level, can't see outside, so he has no idea of what's happening in the world around him. And if I ask Bob how fast the flashlight is moving, Bob will tell me that the flashlight is moving at 25 miles an hour because he threw it away from him at 25 miles an hour. But if I ask Karen how fast Bob was going, she'd say Bob is going 100 miles an hour. She can see the train. She sees Bob in the train. He's moving at 100 miles an hour. And if I ask Karen how fast the flashlight was going, she would say the flashlight is going 125 miles an hour. Because Bob's moving at 100 miles an hour, the flashlight is moving away from him at 25 miles an hour. So the flashlight must be going 125 miles an hour. So Bob and Karen have different answers, but they are both correct because they have different frames of reference. So that is very simple, easy to understand Galilean relativity. Now let's get into special relativity. Okay. This time Bob is in a rocket, and the rocket is going at 200,000 kilometers per second, which is roughly 2/3 the speed of light. Okay? And he has a flashlight, and his flashlight is working this time. And when he turns the flashlight on, he can see the photons moving away from him, and he can measure them. Now, you remember what Einstein said, that in special relativity, that the speed of light is always the same, regardless of the speed of the observer. So since the speed of light is 300,000 kilometers per second, Bob is seeing the speed, the rays move away from him at 300,000 kilometers per second. So he's in a rocket ship. It's moving 2/3 the speed of light, and the flashlight is turned on, and the photons are moving at the speed of light. Now, let's imagine that Karen, okay, let's get back here. Let's imagine that Karen is sitting in a space station and she sees Bob's rocket go by. If I ask Karen how fast Bob was going, she would say Bob is going at 200,000 kilometers per second, 2/3 the speed of light, because that's how fast the rocket is going. If I ask Karen how fast the photons were going, she would tell me that they are traveling at 300,000 kilometers per second, the speed of light. Now, if you remember back to Galilean relativity, if we look at the screen, in the case of the train, we added Bob's speed to the flashlight speed, and we got the total speed of the flashlight. But in this particular case, Karen is seeing the photons of light move at 300,000 kilometers per second, because that's what Einstein said. Einstein said, when you look at something moving at the speed of light, these photons, you're going to see them at the exact same speed, no matter who the observer is, no matter how fast the observer is going or what direction they are traveling. So in this case, both Bob and Karen are both seeing the photons of light moving at 300,000 kilometers per second, even though Bob is moving in the same direction as the photons of light. So the question is, how is that even possible? How can these two people see the same speed for the light when one of them is actually traveling in the same direction of light, but he's measuring it the exact same way? There are two answers to that. And it wasn't spelled out in Einstein's paper on special relativity, but as soon as his paper came out, people said, well, this must be true. The answer is time dilation and length contraction. Okay? In time dilation, the closer you get to the speed of light, the slower your clock is running. So if I had a stopwatch and I clicked it off and I'm watching it go, tick, 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 and I start to speed up, that I will still see the same tick, 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 tick. I won't notice a difference. But if there is another person who is not moving, and I compare my watch to theirs, my watch goes slower. To give you an example of the same thing, if we have two twins that are on Earth and one of them flies away from Earth at 85% of the speed of light, and then gets out, 5 light years away and turns around and comes back, when the second twin comes back, they are younger than the first person, because their clock, because they were moving closer to the speed of light, their internal clock goes slower. Okay? So that is time dilation. The other thing is length contraction, and that the faster you get, the closer that you get to, oh wait, raised a hand. This is interesting. Somebody raised a hand, so.
Yeah, feel free to go ahead and he's muted. So go ahead and ask your question, Jason.
Hey guys, yeah, my question about time dilation. If things are relative, who is the one that's going closer to the speed of the light? I mean, wouldn't we be going close to the speed of light relative to the astronaut that left for a period of time?
So that's a great question. In fact, that is often referred to as the twin paradox. In that if you have these two twins and one of them is going at the speed of light, if you remember earlier when I said there's no fixed point, so anybody can say that their frame of reference is the correct frame of reference. Okay, so the reason that it's not actually a paradox is because there is a limit in the universe, which is the speed of light. You cannot go faster than the speed of light. So when we state the problem that one twin is not moving and the other is moving at 85% of the speed of light, that becomes a hard fact in the statement of the problem. We state that the twin is actually moving at 85% of the speed of light. What is interesting is both twins would measure each other as going slower. But what would happen is, as the first twin goes out, they are in one frame of reference. When they get and they turn around and they come back, they are actually in a different frame of reference. So it's very hard to explain here because it's actually probably a half an hour explanation. But what happens is there's actually a time jump there, that when that twin gets out and turns around, because they've changed their frames of reference, they're actually a giant jump of time where all of a sudden it looks like they are younger, and that's how it's accounted for.
Interesting. So when they get back, if they both had the pocket watches that were identical, when they actually come back, would the pocket watches be the same, or would one, would the younger one actually be a little bit behind the
younger one? The younger one's pocket watch would show how much younger they are. So the watches would not, and they've actually been experiments like this where they take two atomic clocks and they take one and they put it in a plane that flies around the Earth. So the one that's flying around the Earth is going faster than the one that is sitting. And when they compare the two atomic clocks to each other, the one that flew around the Earth is showing a slower time. It has actually ticked off less time than the one that just sat still on the Earth.
All right, we'll have to do some talk, go through that paradox.
I'm sorry?
We'll have to do that for your next talk, go through that paradox.
Yes, I will. That's an entire hour-long talk in itself. So let's get back to length contraction. I'm going to give you two different examples of length contraction because it's kind of weird. If you got in a brand new car in New York City with 0 miles on the odometer, and you drove that car to Los Angeles, when you got to Los Angeles, your odometer would say roughly 3,000 miles, because that would be the distance that you traveled from New York across to California. If you were to get in the same car at 0 miles, with 0 miles on the odometer, and you were to travel across country at 86% of the speed of light, using the exact same roads that you used in the first car, your odometer would say that you traveled 1,500 miles, 1/2 the distance. And it wouldn't be a trick, and it wouldn't be wrong. It would actually be correct and accurate. You would actually only travel 1,500 miles. When moving, as you begin to approach the speed of light, or the closer you get to the speed of light, the length in the direction that you're traveling begins to contract. To give you another example of that, if you had a train that was 2 kilometers long, and there was a mountain that had a tunnel going through it, and the tunnel was exactly 1 kilometer, if you were traveling at a normal speed, as the train is going through the mountain, you'd always see half the train. You might see the back half of the train, as the front half is going through, and then you might see the beginning and the end, and then as it comes out, you see the front half of the train until eventually it got through. But if that same train was traveling through the mountain at 86% of the speed of light, it would disappear inside the mountain. The train is a 2 kilometer train, but moving that fast, space itself, the length of space contracts. And it's interesting, it only contracts in the direction of travel. It does not contract in all different directions. So if you really want to lose weight, just go really fast, somewhere near the speed of light, unfortunately, you'll only be skinnier in one direction. You'll still be the same size in all other directions, but it's something you could give it a try if you were interested. So that is the explanation for the difference between Galilean relativity and special relativity. With time dilation and length contraction, that explains how these two different observers can see light traveling at the same time, even though they have completely different references for it. Now, one of the really weird things is that as you approach the speed of light, if you are in a different inertial frame of reference, completely different inertial frame of reference, you may not see events happen at the same time. To give you an example, if I went to a baseball game, assuming that they were actually happening, I would see a pitcher throw the pitch, and then I would see the batter swing the bat, and then I would see the ball go over the fence for a home run. I would tend to see those events in that exact order. First the pitch, then the bat, then the home run. But somebody who is in a different frame of reference from me might see those events in different order. They might see the home run first, then the pitch second, and then the swing third. It has to do with the way that you experience the events from your frame of reference. And I'll give you an example of how that you might be able to understand it better. If there was a train, let's take Bob and Karen again, a train that is traveling along the track, and just as it passes in front of Karen, two lightning bolts hit the train. One in the front of the, get my hands there. One in the front of the train and one in the back of the train. And the train is going at, let's say, 50% of the speed of light. Okay? Now, Karen, who is watching this, she sees the two lightning bolts hit the front and the back of the train at exactly the same time. So in her frame of reference, the lightning strikes simultaneously. Now, Bob, who is in the train that's going 50% of the speed of light, what happens with him is the lightning that's in the front of the train, he is moving toward that event. So he is going to experience that event quickly, more quickly than the event that is in the back of the train, because he's moving away from that event. So that event has to catch up to him, and he's going half the speed of light, so it's got to really hurry up to get him. So it's eventually going to reach him. So he's going to see the lightning strike in the front first, and then he's going to see the lightning strike in the back, because he is moving so quickly toward the front event and away from the back event. So that's kind of a simple example, but you could take it to its ultimate extreme, that somebody who is on the other side of the universe, traveling at different speeds in a completely different frame of reference, could actually experience any combination of events that we have in any order possible, and theoretically possible. So even though, I know for a fact that I'm going to die after I was born, because I've already been born and I'm not dead yet, there are other people in the universe who might actually see me die before they see me being born. Kind of a strange fact of special relativity. So the final thing that I want to touch on is the question, why can't we go faster than the speed of light? Why does light have a speed limit? One of the things that you might have been told in the past is that at the speed of light, your mass becomes infinite. That's a very common teaching, especially in high school physics. And unfortunately, it makes you think like, oh my great, my head's gonna like blow up giant size and I'm gonna be this huge monster or something. Completely untrue. Not true at all. It has nothing to do with your mass becoming infinite. Your mass does not become infinite. It's an impossibility. Your mass always stays the same as your mass. What does happen is your inertia becomes infinite. And to explain that, I'm going to use something called momentum, because momentum is a very common thing. It's very much like inertia. It's basically how much force it would take to change the direction and the speed that you're traveling. So the formula that they teach you in physics is your momentum, which is P, is equal to your mass times your velocity. So if you had a freight train filled with coal that's 2 miles long, moving very slowly, 5 miles an hour, it has a lot of momentum. The velocity is slow, but the mass is huge. I mean, these cars are filled with coal, so tons of momentum. The same thing for a bullet coming out of a gun. The bullet has very small mass, but it has a lot of velocity. It's coming out of that, it's coming out of the barrel really fast. So that's the formula that they teach kids in high school and introductory physics in college. Your momentum is mass times velocity. But they kind of purposely skip something there. What they skip is called the gamma or the Lorentz formula, so the Lorentz factor. Okay. Okay. So there was, let's go right, there was a physicist named Henri Lorentz, who was actually a good friend of Albert Einstein's, and it greatly influenced Einstein's theories on special relativity. Lorentz was brilliant, but a little bit crazy. He basically spent the latter part of his career trying to prove that we exist in this ether, which is a very Greek idea. The early Greek scientists thought that everything was an ether, some sort of invisible thing that we're floating in, kind of like a water or something. And so Henri Lorentz was trying to prove that we exist in an ether, that the ether is real. And he actually came up with this formula that could calculate the effect of moving. The faster you move through the ether, the more it affects your momentum and your mass. Okay? And so the actual formula that you should have been taught, or that should have been taught, is that your momentum is gamma, which is the Lorentz factor, times mass times velocity. And so the closer you get to the speed of light, the larger that gamma is. To give you an example, the fastest object in the universe, man-made object, is the Parker Solar Probe, which is sent out, God, I can't remember when it was sent out. But anyway, it is traveling right now at about 440,000 miles per hour. So its Lorentz factor at a speed of 440,000 miles per hour, its Lorentz factor is 1.00000002. So the fastest thing that man-made thing in the entire universe, basically its Lorentz factor is 1, which is why they don't teach that in high school and beginning college physics, because there's pretty much nothing that you're going to be doing calculating that you need to worry about how fast you are going in relationship to the speed of light. It's only when you actually get into theoretical physics and quantum physics that becomes super critical, because then you can imagine things traveling that fast. And in fact, light itself, electromagnetic radiation, which includes, visible light, microwave, X-rays, cell phone waves coming out, radio waves, TV waves, they're all electromagnetic radiation moving at the speed of light. So one of the things that this means is that the Hubble telescope was able to measure the cosmic microwave background, which was electromagnetic radiation that was created at the Big Bang. Right when the Big Bang started, there was a period of inflation, and there was all this plasma, and this microwave radiation just got blasted out into the universe. And so the Hubble telescope was actually able to measure that radiation. And obviously if you accept the Big Bang theory, which that's the kind of the common theory in physics, is that happened 14 billion years ago. So that microwave background, those electromagnetic radiation waves, would had to have traveled for 14 billion years over a distance of 14 billion light years. But if you remember, it's traveling at almost the speed of light. And so its Lorentz factor would be incredibly high, which means its time dilation would be incredibly small and its length contraction would be small. So for that microwave background that came from the big wave and Big Bang and hit the Hubble telescope, even though we say that it took 14 billion years to travel across the universe to get to the Hubble telescope, as far as that microwave is concerned, it only traveled for less than a second. And the distance that it traveled was like that much. Like it didn't measure itself going 14 billion light years. It measured itself going that much because it was going at nearly the speed of light. So its length contraction was so great that it took 14 billion light years and got it down to something that I can't even make my finger small enough to measure how small that is. Okay? So, like I said, the good news is you don't have to worry about going anywhere close to the speed of light because, you know, your Lorentz factor for the rest of your life is going to be 1. So you can pretty much use all the simple calculations that they had in all the physics that you've learned until you want to start studying quantum mechanics, and then you're going to have to figure out how to calculate the Lorentz factor. But again, it's actually a pretty simple calculation. So with that, I am now at the question and answer session. Does anybody got any questions? No, Tiffany, you're mute. Oh,
Yeah,
you're
looks like Mark has a question. Go ahead, Mark.
Okay. Is Mark muted?
No.
No.
Mm-mm. Can you hear us, Mark? Okay, does anybody else have a question?
I see Nick's got a question in the chat.
Go ahead, Nick.
Yeah, I thought you would see it there. Is 85% of the speed of light, is that like a magic number? I mean, does it have to be over 50% or something like that?
No, so if we go and look at the Lorentz formula, let me get back to a slide. Get back, no. I have a slide, actually. So this time dilation slide shows, so I use that 86% just because that roughly translates to a 50% time dilation and length contraction. So it's kind of an easy number. It's a halfway number. But if you actually look at the way the Lorentz formula is applied, what you'll see is you have to get pretty darn close to that speed of light before you even start to begin to feel any effect of the Lorentz formula.
Right.
Anybody else? Yep, Tareen, did you?
Hang on, let me unmute her real quick.
Okay.
Where is she? There she is. Go ahead, Tareen.
Okay, so other than for quantum physics and all the really nifty out there stuff, is there a practical relevance or application of Einstein's special theory that is a bit more relatable for those of us that are not quantum mechanics?
Let me see. Let me just go back. You know, I'm trying to think of something that one of the things that is fascinating about the world is that everything moves slow except for light, which moves at the speed of light. So it's almost this dichotomy of if everything that we know and see is like this tortoise, like incredibly slow, nothing, and all of a sudden there's this electromagnetic radiation, which again is visible light, microwaves, X-rays, gamma rays, TV stuff, all those. and they can only move at the speed of light. It can't move slower. If it moves slower, then it becomes mass. It actually it actually begins to take on mass, which it can't do, and so it must move at the speed of light. So there's like this huge world of all of these things, this electromagnetic radiation that just moves at the speed of light, and that all the rest of the stuff that we have that just doesn't even come, like not even anyway close. Like I said, the fastest thing, the man-made thing, the Lorentz number is 1.00002. It's like we couldn't get anywhere near the speed of light if we tried, and that's basically what we can't do now. I mean, there's always things like, you know, warp drives where we're warping space and moving faster and stuff, but they're all theoretical right now, right? Practically speaking, there's no way we're ever going to get anywhere close to any sort of thing, any sort of speed that we would actually be able to use it for anything.
So like tomorrow when the Saturn 9 rocket goes off to take the astronauts up, fingers crossed, none of this impacts them because they're not going nearly fast enough.
Right. So there is a theoretically measurable impact on them. But again, that measurable impact is so small that it wouldn't even, you know, like I said, the astronauts which are up in the space station right now spinning around super fast around, you know, when they get back, their internal clocks will be slower by 1/1,000,000th of a second or something like that. So there's a question.
This is Harry.
Yep.
An example I can think of is NASA has 2 identical twin astronauts, one of which was in the International Space Station for a fairly lengthy period of time. And when he came back to Earth, they had somehow figured out how much younger he was than the twin that had remained on Earth.
Mm-hmm. Right, and again, it is definitely calculable, but in that particular case, there were also a million other factors of, you know, the effect of gravity on the DNA and all that stuff. So part of it was the actual, you know, stopwatch age, but a bigger part of that was the fact of the effect of the body of all these different of spinning around fast and not having gravity and the greater radiation he was subject to and things like that.
Mark,
can you hear us now? Can you hear us now?
I can.
Yes.
You can hear us now.
Yes.
Okay,
Somebody's-
go ahead and ask your question.
Okay, hold on a second. Let me go get Mark.
Are we back in business?
I've got to jump off, but appreciate it so much, Timmy.
Okay.
Thanks so much for the talk.
Thank you very much.
I'll see you guys soon.
Okay, go ahead.
Okay.
Yeah, Jason.
Okay, go ahead.
Can you hear me now?
Yes, we
Yes.
can hear you.
Okay. Question number 1, you talked about the mass of plutonium in the atomic bomb as being 11 pounds,
Yes, I think 11 kilograms.
11 kilograms, okay. And I heard that substantially less than that was actually fission, something, you know, far less than an ounce.
Yeah, I mean,
because right? Is that true?
yes, I mean, you know, the smallest nuclear weapons they make probably use something around an ounce. Yep.
Well, not necessarily the size of the bomb, but the actual conversion of mass to energy in the context of a bomb is probably less than a Lincoln penny, right?
Yes.
Okay, I just wanted to verify that. The number 2, this goes back to the speed of light in the vacuum. I've always been intrigued at the weird blue glow of radioactive material stored in pools of water.
Yes.
And that's called what? Chernoff radiation?
Cherenkov
And that's
radiation.
actually faster than the speed of light, right?
Well,
But it's in water.
so here's the thing.
Okay.
When we talk about the speed of light, we generally mean the speed of light in a vacuum. What's happening with the Cherenkov radiation is that the waves that are coming out of the particles, the neutrons that are coming out, are moving faster than the speed of light in water. And so that's why they're giving off that blue glow. So the nucleus, or the neutrons that are coming up, are not moving faster than light. They are moving faster than light in water. And so it's the differential between the speed of the light and the speed of the neutrons that it causes this Cherenkov radiation, which causes it to glow blue.
Right. Thank you.
Well, I was really worried this was going to be over my head, and I really enjoyed that. So
Thank you very much. That's kind of the goal of these things,
yeah,
is to get them down to make them interesting for everybody.
yeah, and digestible. I liked your metaphors and things. That worked really well for me.
Great.
Does anybody else have any questions before we sign off? Everyone is unmuted. Feel free to chat.
Thank you, Timmy. I appreciate everything.
My pleasure. I got a million of these talks, so if you ever want to give me a call, I'd be happy to do it again.
Absolutely. I'm sure we will be doing that very soon.
Have you got one on quantum field theory?
I'm trying to think of what I got. I've got one on, no, I have an introduction to quantum physics. So
That's
Yeah, thanks, Timmy. I always love your talks. They're so good.
I appreciate
Really like
the
that.
feedback.
okay.
Okay, well then I will see most of you next Tuesday. I'm sure we'll have Timmy back again very soon.
Okay.
Thanks.
All right. Bye, everybody.
Okay.
Thanks for having me.
Bye guys. Have a good night.
Bye.
Bye.